Welcome to the proof of convergence of Jacobi's algorithm. Now, Jacobi's algorithm, as we have seen it, is somewhat strange. It is like solving a Rubik's cube, cube by cube, but without taking care of the cubes that you have already solved. Now, if I tell you how to take a particular cube to its correct position, and then I tell you how to take another cube to its correct position, and you do both these steps one after another, there is no guarantee that both the cubes will be in their right destination. Because when you solve for the second cube, it is quite natural that the first cube will get dislocated from its true position. Now that is precisely the situation with Jacobi's algorithm. We are trying to kill all the off-diagonal entries one by one. So we first kill one off-diagonal entry and then we try to kill another off-diagonal entry. Now, what's the guarantee that this does not cause the first off-diagonal entry to pop up back again? Is there any such guarantee? Let's see. So here we have one example of a symmetric matrix. Here I can see that the largest absolute of diagonal entry is that minus 29. So in the first step, what we shall do is we shall try to kill that one. So we do one step of Jacobi, the same Jacobi algorithm that we used in the last video. So we have this. So you see that quantity that is supposed to be 0, but it is pretty close to 0. It is 10 to the power minus something very large number. So it is essentially 0. So we have zapped that particular off-diagonal entry pretty successfully. Now suppose I carry out the same thing once again. And this causes that old entry to become non-zero again. So you see, there is really no guarantee that terms that you have, that is entries that you have zapped once, will not pop up back again. And that is what makes the proof of Jacobi's convergence result slightly tricky. So we see that there is no guarantee that the individual off-diagonal entries are going monotonically down to 0. They will keep on bobbing up and down. However, what we can show, and that is interesting, is that the total sum of squares of all the off-diagonal entries, that must go monotonically down to 0. So first let's give it a name. I shall call for a matrix A, a symmetric matrix A, f of A, I am defining a function, f of A, that is equal to the sum of squares of all the off-diagonal entries. I will show that as you plug in different matrices in the sequence that you generate, A, A1, A2, A3, etc., f of An will converge to 0. That will of course show that each of the individual off-diagonal entries must also go to 0 because we are working with real numbers. So if the sum of square goes to 0, each of the individual numbers must also go to 0. We make a simple observation. We are always pre-multiplying and post-multiplying our matrix by orthogonal matrices, those Given transformations, those Given rotations. Now if I multiply a vector by an orthogonal matrix, we know that its norm cannot change. If you merely rotate a vector, you cannot change the length of the vector by just a rotation. So the sum of squares of each of the columns will remain the same after you pre-multiply the matrix by that Given's rotation from the left. Now if the sum of squares of all the columns remain the same, then the sum of squares of all the entries in the matrix must also remain fixed. The same thing, of course, holds for the post-multiplication part. When you are post-multiplying, multiplying from the right by another given rotation, the transpose, the same thing works for the rows. Here, each row will retain its norm square. That is, the sum of squares of all elements in any given row must remain constant. And again, if the sum of square of all elements in each row remains constant, then the sum of squares of all elements in the entire matrix must remain constant as well. And this gives us a very important observation. Each step of the Jacobi algorithm will always keep invariant the total sum of squares of all the entries in the matrix. Since the total sum of squares of all the entries in the matrix remains the same after each Jacobi step, we must be moving around the sum of squares from one entry to another. Because the total is always the same, we are merely redistributing those pieces of masses, we might say. Now we are trying to show that the sum of squares of all the off-diagonal entries will go to 0, which basically means as you are redistributing these masses, more and more mass is being accumulated along the diagonal, and the off-diagonals are getting depleted and the diagonal is slowly going up. So that is what we are going to show. So we shall try to do certain technical inequalities to figure out exactly how the off-diagonal sum of squares are going down. So we are trying to show that this quantity Fa, which is sum of squares of all off-diagonal entries of the symmetric matrix A, will go to 0. So if we start with our original matrix, suppose I call it A0, then we compute A1 by doing one Jacobi step, then I compute A2 and so on. I want to show that f of an will go to 0, and that will show that each of the off-diagonals must also go to 0. Now let us start a few notations. Suppose this is my matrix A, n by n. So these are the n diagonal entries. In each of these halves we have some entries. Suppose I have capital N many entries in this half, the equal number of entries in that half. So n is actually n into n minus 1 by 2. So if you want, you can have this formula n into n minus 1 by 2. Now at each step, what we are doing is we are picking up that of diagonal entry which has the maximum absolute value. Suppose I call it P. So P is the entry, an off diagonal entry with the maximum absolute value. So P is that off diagonal entry with maximum absolute value. Since it has the maximum absolute value, so we can immediately say that f of a must be less than or equal to twice n p squared. And why is that? Because if I square all the off-diagonal entries, each of them must be less than or equal to p squared, and there are n of them, n on this half, n on that half, so the total can never exceed 2n p squared. So I already have one inequality. Now let us see what happens when I do one step of the Jacobi algorithm. Suppose that we are considering one single Jacobi step. We are at ak and we are moving after a single Jacobi step to ak plus 1. Now how do you carry out the step? In this step we first find out that particular off diagonal entry which has the largest absolute absolute value. Suppose that happens to be in row I and column J. And let that particular entry be P. Once you get that, you look at the 2 by 2 submatrix consisting of these things: the ijth entry, the jjth entry, the iith entry, and the jith entry. So these 4 entries, they constitute a 2 by 2 submatrix, and we are interested in only that. We apply our Gibbons transformation to only that particular submatrix. Everything else is remain unaffected. Now we have to understand this carefully. When we apply that matrix multiplication from the left, everything in this row and this row might change. I know that I am turning this into 0, so this will become 0, but as a result, these numbers in these rows will also change because I am pre-multiplying. So if I take any linear combination of these two, the same thing is applied to all the other entries in these 2 rows as well. However, every other row will be completely unaffected. Similarly, when we are post-multiplying, then all the entries in these 2 columns may change. However, the entries in the other columns will remain unaffected. Now let us see how this influences f of ak. So how f of ak changes to become f of ak plus 1. How does that change? Let's consider these 2 entries. When you applied the pre-multiplication, these numbers have possibly changed, but because you pre-multiplied by an orthogonal matrix, so the total sum of squares of these 2 entries must remain the same. They may be redistributed, but the total must remain the same. Since both of them are of diagonal entries, so both of them still remain within the scope of the f function. As a result, any change in these entries will not change f of ak. Same is true about these 2 entries, both being of diagonal. Same is true about these entries. The only exception will be these pair and these pair. Whenever you change these, you are moving part of the mass from the off diagonal to the diagonal. Since f keeps track of only off diagonal, as a result, f will go down. The same thing may be said about the columns. Any change in these 2 entries will leave the f function unaffected. So how does it change? This off diagonal entry p will become 0, and there the total sum of square will lose 1 copy of p squared. Similarly, this p will also become 0, and there we shall lose another p squared. So f ak plus 1 will be f of ak minus 2p squared. Now remember that p was the entry with the maximum absolute value among all the off diagonals in ak. As a result, by the argument that I have already mentioned, this must be less than or equal to twice n p squared. Remember, n is the total number of off-diagonal entries on this half, which is also equal to the total number of off-diagonal entries on that half. So twice n is the total number of off-diagonal entries. So you see, p squared must be greater than or equal to f a k by 2n. Now put the 2 things together and you can see how f a k plus 1 will be changing. That is equal to f a k minus this. So this will be less than or equal to f a k, the 2 and this 2 cancels, minus f a k by n. This was greater than equal to, but this became less than equal to because I have a minus sign here. And that is 1 by 1 minus n, 1 minus 1 by n, f of ak. This quantity is strictly less than 1, which shows that at every step f of ak plus 1 is basically coming down. So what it says is that f of ak plus 1 must go to 0. And this factor being strictly less than 1, it will come down at a geometric pace and eventually approach 0. And that will complete the proof that all the off-diagonal entries must individually approach 0.